Hello students. In the previous video we discussed about the dissolution controlled drug delivery systems. Today we are discussing on the diffusion controlled drug delivery systems. What is diffusion control systems? These are the systems where the rate controlling step is not the dissolution rate of the drug or release controlling element, but diffusion of the dissolved drug molecule through the rate controlling element. And this rate controlling element can be either an insoluble or non-erodible or a non-biodegradable materials or the polymers. So what is a dissolution control system first of all. In the dissolution control system, we discuss about the dissolution of the drug molecule is limited, where in this situation of diffusion control delivery system, the diffusion or the movement of the dissolved drug molecule is being controlled. Movement from where to where is controlled. That is, the movement of the drug molecule present in the core. If you consider a tablet, if you consider a control release drug delivery system as a tablet, the tablet inside, the core of the tablet is having the drug substance. The movement of the drug from the core out to outside the core, this transport we call it as the diffusion. So the process of this transport is being controlled in the diffusion control drug delivery system. So in this case, once if you administered any of the control release tablets, once the tablet reached into dissolution fluid, once the tablet reached into your stomach, wherever it might be, either the dissolution fluid or the gastric fluid may permeate the membrane of the tablet. It reaches into the core of the tablet. This dissolution fluid may solubilize the drug inside the core. Now, till this step might be a faster, or this steps may be happening very easily, but once the tablet is dissolved, the movement of the dissolved tablet within the core or from the tablet into outside the tablet is being controlled. This transport is a slow process, and since this transport is a slow process, this forms a control release drug delivery system, and this is happened with the support of either an insoluble, non-erodible or a non-biodegradable polymers. It is, however, porous in nature and allows diffusion of the dissolved drug. That is, the membrane, the core, the tablet we made with a non-erodible membrane, but this membrane has a characteristics that it is porous in nature. Because of this pores present in this membrane, this pores allow the movement of the dissolution fluid from outside environment into the inside environment, and this solubilize the drug molecule, and again this porous membrane can allow the movement of drug molecule from the tablet or from the delivery system into outside the system. Now, depending on the mechanisms of the rate controlling element, the systems can be classified into two categories. They are, first one is a reservoir system, also known as porous membrane control system. Second one is a matrix system, where that is also known as porous matrix controlled drug delivery systems. First, let us see what is a reservoir system means. In the system, water insoluble polymeric material encases a core drug. Drug will partition into the membrane and exchange with the fluid surrounding the particle or tablet. Additional drug will enter the membrane, diffuses to the periphery and exchange with the surrounding media. So in the first class of control release drug delivery system, we explained what is a reservoir system and what is a matrix system. So the reservoir system is the one in which the core of a system is being covered with a polymer, or this polymer forms a boundary. Polymer forms a boundary of a tablet. That means a tablet is being covered, or the delivery system is being covered with a rate limiting polymer membrane. So such type of system we call it as a reservoir system. That means the boundary of the system keeps the molecule, keeps the drug substance inside it. Suppose if we consider a water tank, the boundary of the water tank keeps the water inside. If we consider a dam as a reservoir system, the boundary of the dam may keeps the water inside. So the same way, if we consider the tablet, a quarter tablet, this coating keeps the drug molecule inside the tablet. So this such a system, we call it as a reservoir system. So within the system, within the reservoir system, this drug molecule can easily move, whereas it cannot penetrate the boundary. That is the case in the case of water reservoirs also. Within the reservoir, the water can freely move, but this water cannot permeate the boundary. The water cannot permeate the dam. So this way the reservoir system also having the same functionality in which within the core the drug molecule can easily permeate or easily move, whereas it cannot permeate the membrane. So that is a speciality of this reservoir system. So in this case, a water insoluble polymeric material, speciality of this water insoluble polymeric material encases a core of the drug. So drug will partition into the membrane and exchange with the fluid surrounding the particles of the tablet. You have studied what is partition coefficient in the previous years. Now that was a partition coefficient, that means the partitioning of drug between the oil and the water. That was the partitioning of the drug between the oil and the water. But here we are discussing about the partition coefficient between the membrane of the delivery system and the core of the delivery system. The partition coefficient between the membrane and the core. That means the drug that is present in the core will partition into the membrane, and from the membrane again it will moves into the surrounding environment. Such partitioning from the core into the surrounding environment is what we are going to discuss here in this reservoir system. Now here is the demonstration of the diffusion rate controlled the reservoir systems. In the first, you can see the spherical drug delivery system. Inside the spherical drug delivery system, we can see fine drug molecules are being incorporated. So the characteristics of the drug molecule is a soluble drug molecule, and the membrane outside it, you can see the membrane. The membrane is porous in nature. So through this pores, this micro pores, the water is influxing, water is moving into the core, into the tablet. This water molecule will solubilize the drug molecule, and the solubilized drug molecule again comes out through the pores into the surrounding environment. So that is the second picture. You can see second part of this picture. You can see in the first part the drug molecules are inside the systems, whereas in the second part, to the pores, the water channels, water molecules entered in the core, it dissolves the drug molecule, and the drug molecules comes out of the delivery system. Now the equation governing such a reservoir system is given by the equation flux represented by J. So J is equal to minus of D, it's only minus of 1D, minus of D into dc by dx, minus of d into dc by dx. So dc by dx, as you know, that is the change in the concentration gradient, where J is the flux, the capital D is known as the diffusion coefficient, and dc by dx is the change in concentration with distance x. So here x represents the distance. So this is the equation that governs the movement of drug molecule from a reservoir system. So in terms of amount of the drug, the equation can again be rewritten as dm by dt is equal to a dk delta c by l, dm by dt equal to a dk delta c by l, where a is the area, d is the diffusion coefficient, k is the partition coefficient, l is the diffusion path length, and dm by dt is the amount of drug released with respect to time, that is dm by dt. So that is, from the reservoir system, the amount of drug released with respect to time is equal to A dk delta C by L, where A is the area, D is the diffusion coefficient, K is the partition coefficient, delta C is the concentrational difference across the membrane, and L is the path length. So what is meant by the path length here? The path length is the length from the core into the surrounding, the distance traveled by the drug molecule from the core into the surroundings is considered as the path length. So based upon this, the partition coefficient is one of the important parameter that can affect the transport of the drug molecule. That is, partition coefficient is high means the core will be depleted of drug in a shorter time, so that zero order release will be observed only over a short segment of time over the entire course of the release. Second is the diffusion coefficient and the area, surface area. Now, to obtain a constant release, so now we know what is a control release one. Control release, which releases the drug at a control rate for a longer period of time. Now, if you want to obtain a constant drug release, that is a speciality of the zero order release pattern. To obtain a constant drug release, one of the most critical parameter is the path length, concentration, and the diffusion coefficient. Now, as the time goes, the path length changes. Initially, if you consider a tablet, the tablet surface is having drug molecule. This drug molecule need not to travel for a longer distance, whereas as the time proceeds, the drug is present in the core of the tablet, inside the center point of the tablet, whereas in the initial case it will be somewhere in the edges of the tablet, where the tablet, that is the drug molecule that is present in the edges of the tablet, need not to travel for a longer length. That means it can easily be come out of the system. Whereas the drug molecule what is present in the center point of the tablet, it has to travel in the entire radius of the tablet in order to come out of the system by penetrating this. That's it. The path length plays a major role in to get a constant release. So as the time increases, the path length may be increases, and we may be failing to get a constant drug release after a particular period of time. So that is one of the main drawback of this type of systems. Now, the various methods that can be utilized to develop the systems, which includes the press coating, the air suspension technique, or even the micro encapsulation methods can be utilized for developing the system. So with this system faces certain crucial parameters. So the crucial parameters includes the polymer ratio in the coating, the film thickness, and the hardness of the microcapsule. As you know, the polymer ratio, as the polymer concentration increases, obviously it may limit the permeation of the drug molecules. Now, the speciality of this polymer membrane, as we discussed, it is porous in nature. Now, These polymers, as such, it may not be porous in nature, but in order to provide a porous, we have to add certain porous material to this. One of the main pore former as what here we used in the membrane system is polyethylene glycol. We can use any of the performing substances, but one of the good performer is PEG, that is polyethylene glycol. So these performers may produces or develop certain pores on the membrane, and this pores, through this pores the water influx and the drug efflux happens. Now the ratio of the polymer and with the performer maintains a major role in release of the drug molecule. If the polymer concentration goes much higher than that of the performer, the number of pores will further reduces, and which will again limit the release of the drug molecule. The second factor again, it is film thickness, as obviously as the thickness of the film increases, the drug release obviously decreases. Finally, the hardness of the microcapsules. The hardness of the microcapsule, if you prepare, also can limit the release of the drug molecule, and this is inversely proportional again, that is, as the hardness increases, the drug release will be decreasing. So these are some of the crucial parameters that can affect the reservoir system. The next one is the matrix system. So a soluble drug dispersed in an insoluble matrix, that is a system, that is a soluble drug. So soluble drug always can easily dissolve very fastly, that is the specialty of this. So such type of soluble drug molecules must be developed into a control release technology system by using any of the insoluble matrix. That means the soluble drug molecules are incorporated inside an insoluble matrix system, and the rate of the drug release is depends upon the rate of drug diffusion, not on the rate of drug dissolution. The diffusion of the drug molecule across the matrix material, whereas in the previous case the diffusion of the drug molecule across the reservoir system was the most critical thing, whereas in this case the movement of drug molecule across the matrix is the most crucial or the most critical parameter. And the equation that governs this equation is the matrix system is Q is equal to d epsilon by T into 2a minus epsilon Cs into CST the all raised to 1 by 2. So this is the equation that governs the release of the drug molecule from the matrix system, and this equation is given by Higuchi, and this is the Higuchi's equation. Now in this equation, the Q stands for weight of the drug released per unit surface area, weight of the drug that released per unit surface area. D stands for the diffusion coefficient of the drug. E or epsilon stands for porosity of the matrix. T stands for tortuosity of the matrix. CS stands for solubility of the drug in the release medium, and A is equal to concentration of the drug in the tablet expressed as gram per mole. I'll repeat once again. The Q stands for grams or amount of drug released per unit surface area. D stands for diffusion coefficient. E stands for porosity. T stands for tortuosity, and CS stands for solubility of the drug in the release medium. A is equal to concentration of the drug in the tablet. So in the previous equations and all, A was standing for area, but please keep in mind that A here stands for concentration of drug in the tablet. Now this equation based on certain assumptions. The assumptions are a pseudo steady state is maintained during the drug release. First assumption. Second one, A, that is the concentration of drug in the tablet is always greater than the CS, that is the solubility of the drug in the CS, that is excess solute is present in the core of the tablet. C is equal to 0 in a solution at all times. That means it's a perfect sink condition, or C, or you can call it a CS also. That CS is always 0. That means The amount of drug that is reached from the core into the surface, what is the drug released into the dissolution medium, is always existing as a zero. That means it maintains a perfect zinc condition. Whatever it is being released, it will be absorbed into the systemic circulation, and the drug particles are much smaller than those in the matrix. The drug particles are comparatively smaller than that of the matrix material, and the diffusion coefficient of the drug remains the constant, and no interaction between the drug and the matrix occurs. So these were the assumptions in this huge model, and based upon these assumptions the formula is being developed. Now, these matrix devices can be again of different types. The first one is insoluble plastic matrices, fatty matrices, as well as hydrophilic matrices. So these are the type of matrix material what we used for developing the matrix systems. So the first one is the insoluble plastic materials, where these materials are purely insoluble and the movement of the drug molecule happens only by diffusion of the drug molecule across this membrane. Now, one of the main drawback of the system is, once if you administer the system after a particular longer period of time, after a long period of time, upon mastication of the drug, the drug will be releasing out of the system very quickly. That means this type of insoluble plastic matrices can hold the drug molecule only up to a particular period of time. After that, it will be completely releasing the drug after a particular period of time. Now, the second is the fatty matrices. This consists of the wax material, and these mixtures can be congealed, granulated, or compressed into core. This core may be or further coated, can be coated with any of the polymers also. So again, these fatty matrices are again utilized for solubilized drug molecule or easily soluble drug molecule, which may permeate, which may delay, which or may reduces the permeation of the water moieties. The last one is the hydrophilic gums were used to provide the sustained drug release. So in this method, the hydrophilic gums such as, that is, hydroxypropyl methyl cellulose, carboxymethyl cellulose can be utilized, and the drug delivery systems can be developed by compressing the mixture into tablet or any other dosage forms. Even though it is hydrophilic in nature, it also has the tendency to limit the permeation of the drug molecule across the membrane. Now this is the picture what is showing the two type of the hydrophilic matrices. This is the first one is a non-swellable diffusion rate control ductile system, and the one is a swellable release control system. In the case of a non-swellable one, you can see the picture where in which this, if you assume this as a tablet, inside the tablet there is a drug molecule incorporated within a matrix material. So the matrix material is demonstrated with the vertical lines, and within this matrix material the drug particles has been incorporated. Once the drug fluid is getting into the systems, so in the case of a reservoir system, the reservoir system was made with a porous material. Here you cannot observe any porosity here, but it is purely made of the matrix material. So the water molecule has to penetrate this matrix material, and it has to penetrate the matrix material. It has to reach into the drug moiety, and it has to solubilize the drug molecule. And this drug molecule slowly started transporting across the matrix material, and it is coming out of the surface system. Whereas the shape of the tablet remains the same from the beginning till the end without any swelling. That means even though the drug is being released out, even though the drug has taken up more water, it is not swelling because the polymer what is used to develop the system is a non-swellable polymer. Whereas we have another category of polymers, that is a swellable polymers. So in the case of a swellable matrix diffusion system, what happens is the matrix system, the polymers will takes up more quantity of the dissolution fluids and it swells. Because of its swelling tendency, the drug molecules has been easily released out through this diffusing through this matrix material. So this is the specialty, or this is the difference between the swellable as well as the non-swellable matrix systems. So that's all about the diffusion system. Thank you. So today we have learned about the matrix system. What is a matrix system? Sorry, diffusion control system. And diffusion control system can be of two types, that is reservoir system and as well as a matrix system. We learned what is a reservoir system, what is the equation for the reservoir system, and what are the methods used for preparation of the reservoir system, and what is a matrix system, what are the polymers used, and what are the types of matrix system that can be utilized. So these are the topics what we covered today. So next method for controlling or developing the control structure system we'll discuss in the next class. Okay, thank you.